Hello everyone, welcome to our tutorial titled Recent Advances in Entity Resolution. So in this tutorial, we'll be talking about entity resolution and focusing on recent development, especially using deep learning to solve this long-standing problem. So first, we will actually have a gentle introduction about the problem, its difficulties, and some overview of the recent approaches. Then we actually focus on two distinct aspects related to entity resolution to be presented by the other two presenters in the team. So what is entity resolution? So the entity resolution is trying to identify co-referent manifestations that refer to the same real-world entities from different data sources. So the key part here is that the same real-world entity may have different representations in the computer and in different data sources. And regarding different kind of formats or modalities, you can actually see there is a huge variety of them, and this gives rise to a rich set of problems that we need to deal with. So we give a few examples below. The first example is actually coming from a real dataset widely used in as a benchmarking datasets, where a group of researchers have crawled the Amazon website and the Google shopping website and collect all the information into relational tables. And our job is to identify the same product sold at two different platforms. So as you can see, there are a huge variety in terms of the way we describe them in the schema level, which on the left-hand side, you can see the description, manufacturer, and the price. And on the right-hand side from Google, you only have a title and the price. So not only to deal with the so-called schema difference, we also need to deal with the difference in terms of the textual description, and also the numerical values do not really match in terms of the price. As an example, let's look at the two websites talking about the same real-world person, who is the current president of United States, Joe Biden. And although the text is pretty small on this page, but as you can imagine, the text description roughly talk about a lot of things in common, but not really precisely, identical word by word. Okay, but for human beings, after reading through the both articles, we can be pretty sure that they are actually referring to the same entity. Although Joe Biden is actually, you can argue this is an easy example, but there are plenty of examples for persons with different. There are two scenarios. There are actually different people with the same name, or the same person with multiple names. So these actually adds to the difficult level of the problem. And another example is actually if we move on to the other modality, which is multimedia. You can imagine that for the same person, here we just use some kind of animated icons as example. So assuming that we have two real-world persons, and if we look at all the digital pictures about them, let's say one of them is a celebrity, so there will be a lot of pictures. Each of them actually will be different in terms, if you really compare them pixel by pixel. Not to mention that even for the same picture, if you adjust the lighting slightly or change the aspect ratio or add some kind of watermark, they will actually become different. So this is also one niche part of the entity resolution if we really need to include or mainly focus on multimedia contents. So ironically, entity resolution has many duplicate names, which means all the names we actually mentioned below are actually coming from at least several literatures, actually clusters of literatures, and they decide to use different names for essentially the same problem. This is partly because the problem is so popular, or they exist in all sorts of areas, and the people actually name the same problem using different kind of names without realizing that there is some kind of standard names in other fields. For example, record linkage, as far as we know, mainly coming from statistics and also Census Bureau, and duplicate detection is more related to computer science. So why entity resolution is hard? Not only we show several examples, we look at a few important traits. The first one is that there are heterogeneity. The main problem is that there are heterogeneity everywhere. The first example is that, for example, the name and attributes could be ambiguous. For example, my name, Wang, is actually well known to be highly ambiguous on DBLP. So in fact, DBLP commented that this name is the most ambiguous one among all the names they actually have on their website. So currently, I think there are about 313 Wangs that they can classify, and even with that, there is a huge default cluster of Wang, which I believe they cannot classify into clearly. But even among those already classified, as you can see, all these researchers actually, I'll just list a few researchers who actually work on kind of similar or overlapping areas. And also they have some kind of problem with affiliation as well. In fact, if you look at the last two, the third picture is myself, and I kind of previously and also currently is affiliated with HKUST and also HKUST Guangzhou. And there is another Wang in the CSC department who is actually affiliated with HKUST as well. So you can see that this will create even a more challenging scenario for many of the disambiguation methods. And if you look at the paper titles that each and every Wang actually in computer science have written, there are actually a lot of overlapping keywords like algorithm, data, learning, and the graph. So it's really, really hard to distinguish them just based on the attribute values. So another kind of difficulty is coming from changing attribute names. So as one very simple example, by the way, some of the slides actually coming from excellent survey and tutorials from Luna Xingdong. So basically, this is one example where Anhai Dao is actually one researcher working in this domain as well. And if you look at two different pages from their websites, one actually says the primary organization, and the other page actually says affiliation. So we need to figure out, okay, primary organization actually is the same as affiliation. And this is actually not so simple because we don't have the rights to change their websites, and essentially the website creator have the freedom to set the names. And also this is another example provided by Luna. And as you can see, for the same Mexico celebrity, basically if you go to IMDb and Wikidata, the date of births are not matching with each other. So this is the case for the erroneous values, which means wrong values, or sometimes we also have another problem with the value, which is actually the missing value. So this is again from the real benchmark dataset where the manufacturer of one product, the first one, the Microsoft PowerPoint 2004 Mac Apple, does not have any manufacturer. So basically this will actually create some problem for us to identify, okay, two entities actually, two entity description actually refer to the same entity or not. And even if we are talking about the same value can be represented in different formats. So one notorious example is the dates, right? In America, in Europe, and in, let's say, in Asia, or in many different countries, the default way to represent dates are actually different. And on the other hand, the name is also highly ambiguous. For example, again, using An Dong's example, there are actually different names and name abbreviations he had used in his previous publications, making the problem much more difficult. So there are also another challenges actually, because we need to deal with different data types or modalities. For example, we could pose the entity resolution problem where the data is given in web tables or lists, where we already have this kind of every record or most of the records conform to some kind of schema. Again, in reality, the web tables, as you can imagine, could be actually very hard to parse and to understand. And for example, if you ever look at let's say World Cup results on Wikipedia, they actually have very detailed, sort of like a nested table. It's very hard for an algorithm to automatically parse the data. And it's also possible that the data is presented in about one entity is actually entirely within a page, although we can use XML or DOM tree to represent it, but essentially we need to deal with the semi-structured nature of different entities. And then lastly, but but also very importantly, many times the entities are described using free text, like a paragraph. And within the paragraph, there are actually a lot of entities mentioned. And in fact, this is also called entity linking problem, or NEL problems. And it has also been studied in a lot of research papers. So in this tutorial, we'll focus on machine learning-based approach to solve the problem. So while using machine learning, I think I just want to emphasize that if you compare machine learning with the traditional programming, the traditional programs, actually the human is responsible to handle all the logics, and they actually generate some kind of output based on the input data and the written programs. But machine learning makes it adaptive. It actually can, through some kind of training, or if you like, some kind of experience or some kind of trials, they can actually adapt to the data and the sample training label results, and they try to make sure that the program, they actually spit out a program such that the program actually can work reasonably well for similar distributed data. So it's well known that deep learning is actually one of the most successful subfield within machine learning or AI. And you can see that it mainly consists of some machine learning models, objectives, and optimization methods. And why deep learning actually helps in this problem space, we argue that it actually can address many of the previously mentioned challenges. For example, it bridges the vocabulary mismatch, for example, different name variations and schema name variations. So if we have, nowadays we actually have pretty good pre-trained language models and also summarization method or embedding method, such that, okay, for these different surface type, text with similar context, but similar semantics, but different representations, there is a high chance that they will actually come down to nearby embeddings or points in a high-dimensional space. Hence, we can identify the high similarity among them. And also, better generalization, because if you look at last point, if we really train the model well, basically it can generalize to unseen examples. This is also one big problem in the sense that in the traditional rule-based record linkage or entity resolution, it's really hard for human beings to come up with a method which deal with future, unseen examples. So this slide actually summarizes roughly all the major papers and their corresponding deep learning models that we are going to cover later. So as this actually shows a brief history of entity resolutions. I won't go through them in detail, but just to mention that roughly around 2015, people start to use sophisticated kind of machine learning methods, and circa 2017, people actually start to use deep learning based methods. And within the deep learning methods, we are going to look at several different ways to deal with schema and the values and the models. Okay. So finally, let's have a quick tour about the major steps in entity resolution. So the input are the data from different sources, and for simplicity, in many cases, we assume that the input are in this kind of relational tabular format, which is most likely the case in especially in organizations or in commercial applications. And the first step we need to deal with is that because the relational schema or the tables may have different kind of schema, so we actually need to do this kind of schema alignment. And then suppose we need to do the matching in the next step. The matching will actually try to find co-referent tuples from different tables. But in order to improve the efficiency, we actually need to add the blocking step in the middle. So in the schema alignment, we show one example where, again, using the Google and Amazon example, we actually need to identify some of the attributes are actually with different schema names, essentially refer to the same semantic columns. Okay, so this is the schema mapping. And the second step is blocking. So blocking is trying to group tuples pairs into blocks such that we only need to do the matching within each blocks. This is essentially trying to reduce the number of comparisons we need in the matchings, and this step is quite crucial to scale up the entity resolution to large datasets. And the last step is actually the matching. So within each blocks, we actually try to use models to determine whether the tuples actually refer to the same objects. And this is the current state-of-art method usually uses deep learning models which integrate.
Hello everyone, my name is Yaoshu Wang, and we discuss some methods of entity blocking in this section. So the problem definition is that given two relational tables A and B with the same schema, we aim to find all tuple pairs that refer to the same real-world entity. There are mainly four measurements to evaluate the performance of anti-blocking methods, including pairs quality, reduction ratio, running time, and pair completeness. So we mainly classify these methods into two categories. The first one is the non-learning methods, such that some learning strategies are written by a human themselves or by some heuristic algorithms. There are some baselines, including hash-based methods, sort-based, size-based, and schematic-based methods. Also, some algorithms are proposed to improve this baseline, such as meta blocking or rule-based blocking. The second category, is the learning methods, which are our main focus. So the setting is as follows. So given a set of labeled instance, we aim to learn some learning strategies for entity blocking. there are mainly 4 directions, including learning rules or learning non-deep learning models such as random forest or logic regression. The third one is the learning repetitions, such as we transform each tuple into the Euclidean space. The final direction is the learning hashing. Similarly, we transform tuples into the Hamming space. First, we briefly introduce some methods of learning rules. The first method is the pros DNF, and the rule is based on the disjunctive normal form, DNF for short. And DNF relies on predefined predicates such as Jacquard, cosine, exact mesh, and also on. So the author transformed the learning problem to the red-blue set cover ones. So each predicate is assigned to one binary value W, and the objective is to make sure that the selected predicates should not satisfy many negative pairs, but should satisfy as many as positive pairs. So in experiments, the PROS-DNF shows that it has smaller reduction ratio and higher recall than other baselines. BSL and BSL Plus also rely on DNF, and also the authors also transform a learning problem to set cover one. Different from a PROS DNF, their objective function is to minimize the reduction ratio by using labeled and unlabeled data. Their condition is that the recall should be above a predefined threshold. Fisher is also a rule-based learning method, but it is unsupervised. The main contribution is to automatically generate the training instance. In summary, the author set two values, a lower bound and upper bound. So in this region, whose similarity are higher than the upper bound, some total pairs are selected in this region, such as they are considered as the positive pairs. Also, some negative pairs are selected in this region, but they also discard some total pairs with very small scores, such as 0. So in experiments, the feature shows that the recall is 25% higher than the unsupervised baselines. GBF is also another rule-based learning method, different from a previous one. It depends on a new rule, a general Boolean formula, because it is more powerful. However, finding valid GBF is not an easy task because it has larger space. Large number of objects, and if some predicates are similar function, thresholds are known and should be learned by some methods. To solve that, the author used the iteration procedure. So first, they generate some intermediate GBF, and this intermediate GBF is verified in the whole dataset to check their correctness. If they are invalid, and they eject some counterexamples to fine-tune the intermediate GBF or regenerate a new one. The iteration terminates if optimal GBF are found or the round reach the maximal iteration. So the learning GBF is interpretable and compatible with tree-based methods. For tree-based methods, although they can also be considered as rules for each part, but they are very complex and hard to understand by humans. So the advantage of EM-GBF is that the GBF has the compatible performance, and their rules, the GBF rules, can also be understood by humans. Hybrid MD is also anti-blocking method, but it is based on the mining instead of learning. The rule is the matching dependency rules. The objective is to mine all minimal MDs based on some interesting measures, such as the large false or high confidence. Okay, to find all valid rules, they use hybrid search methods, which combines the line-wise and depth search manner to improve the performance. The hybrid MG shows that they have high precision but relatively low recall, and the F1 is not higher than the random forest. So now if we use the previous method to generate some learned rules, so next problem is how can we efficiently find all satisfied two pairs from tables A and B using these rules. Firstly, we consider the first case. If the rule is one single similarity function, for example, if the rule is the Jaccard similarity and the threshold such as 0.8 is learned by the previous methods. So we can use the prefix and count filtering as follows. Firstly, we transfer each tuple in A and B to signatures such as kilogram, chance, or variance. Secondly, we use prefix count filtering with inverting index, such as if two tuples are similar enough, and they should be placed in at least one bucket. And then we adopt condition product in each bucket of inverting index and verify these pairs using the theoretic function. And the second case is that if the rule is one conjective query of several functions, such as the rule is contains two similar functions in this example. So we can use multi-attribute similarly join methods, which is the method in CMON 15. So the highlight idea is to construct an optimal prefix tree, and each level is one similarly function, and the node donus represents a signature. So if two tuples satisfy a rule, and they should be placed in at least one bucket. Okay, the third case is that if the rules are more complex, such as the GBF, DF, or matching dependencies, or we can also use the error detect methods, which is a VLDB paper. The highlight idea is to extend the hypercube such that if two tuples are matched, they should be placed at least in one cube, and then we distributed this cube to workers, and each workers and independently handle them. Okay, and now we discussed the non-deep learning model. We use the Smurf as the example. The Smurf is to learn a tree-based binary classifier such as decision tree and random forest. And the objective is to find all tuple pairs that satisfies the random forest. So they first sample some data and they label them using an active learning manner and learn a random forest. Then they extract the blocking rules and find the tuple pair that satisfying it. And finally, the candidate set C is the result of identity blocking. So the Smurf has higher accuracy than the rule-based methods, but the blocking. Third, then we use some deep learning-based methods. So here is figure is converted to an dense relation, and then we use a classifier, including semantic layer, dense layer, and the softmax layer to output the final binary decision 0 or 1. And so after each tuple is transformed to the embedding, and they use the LSH strategy to accelerate the blocking procedure. So if two So if two vectors are close to each other, and this would be assigned to the at least one bucket. So tuples in the same buckets are considered as candidates. So the RSH is mainly based on the hyperplane RSH. Also, to increase the recall, and the paper also considered multi-probe RSH to increase collision of similar tuples, and such as with it is very high probability that matching tuples are assigned to this same buckets. Sentiment board is very popular in the NLP area and widely used in the industry. The highlight idea is that it also uses Siamese methods, but they replace neural network with a BERT, which is a pre-trained model. They only need to fine-tune it in the downtown tasks. So see this figure. If two sentences or tuple A and B are similar or match, so the cosine similarity of their embedding should be very high. So because BERT is a pre-trained model, so it is the accuracy is better than the SOTA embedding method. But from our experiments, the accuracy is worse than some matching models, which we'll discuss later. DER blocking is the latest work in the entity blocking problem. So this figure shows the general framework of DER blocking. So for each tuples in the relational table, we use the word embedding such as GLAW or FastTest to transfer each word or subword into embeddings. So, and then each sentence is transfer a matrix. And then after that, and we use a neural network model by some strategy such as self-production, cross tuple training, triplet loss minimization, or a hybrid strategy to transfer the matrix into a tuple embedding. And then we used vector-based pairing methods such as hash-based, schematic-based, or compositive pairing methods to find the similar pairs, which generates the final candidate set. So in the following, we mainly discuss how to transform the matrix to the tuple embeddings. So the first method is the SIF. So for each tuple, we calculate a weighted average over the word embedding or embeddings to obtain the aggregation vector. The VT is the aggregation vector. FW is the weight. And then we use the PCA and calculate the tuple embedding for each tuple by subtracting the subtracting the projection of its aggregation vector over the first principal component, and the UT is the final embedding of the tuple. So SIF is often considered as an aggregator. The second model is the autoencoder, which is an unsupervised model, such as it does not need label data. So we can also use the aggregator such as SF to transfer the matrix into a representation, and then we use the encoder and decoder to transfer the embedding to a hidden representation, which are more compact by using the reconstruction loss. So the hidden representation is the final the embedding of the tuple. Okay, we can also so in the autoencoder, the encoder and decoder are implemented by the feed-forward network. Okay, but we can also replace the feed-forward network of encoder and decoder with transformers, which we'll discuss later. The DR blocking also adopt a second-to-second model to replace the computation. So yeah, the former is replace the floating layer to improve the performance. In this case, we discussed which contains four components. The first one is the scale dot product attention, which often includes three metrics: QKV and the softmax. To improve the performance, and the transformer used the multi-head attention and position-wise feed-forward networks. But because transformer did not know the position of each word, so it adds the positional encoding to record this information. So also, by using transformer, the final representation is the embedding of the first word of the tuple, namely CRS. There are also some methods to improve the autoencoder. So this is CSAE is to add context information into the autoencoder, such as X is the original data and HC is the context information. The loss is the reconstruction loss of both the original data and the context information. So H is the dense representation of the original data and the context, and it's more powerful. OVED is also on the paper that adds an extra variational attention in the second-to-second model. So this term is the loss of the rational attention. Oh, let's go back to the DER blocking. So the next strategy is the cross-tuple training, CTT for short. So the main idea is to automatically generate label data for positive pairs. So it's like some tuples whose overlaps of words should be at least 60%. And for negative pairs, we randomly select one tuple from the dataset for a given tuple, and the tuple pair is considered as the negative one. The model structure is similar with the Siamese network, such as aggregator is used to transfer the matrix to one representation, and then we use the Siamese summarizer to transfer each embedding to a final dense representations, which donates the representation of each tuple. The classifier is used to predict the binary decision. Two loss functions often used. The first one is cross entropy loss, which are widely used in binary classification problem. Triple loss is more efficient in some representation model. The idea is that the distance of embeddings of positive pairs should be much smaller than the distance of negative pairs. Also we can replace the classifier with cosine similarity, which we call CTT cosine. The final model is the hybrid model, which combines the CT and the autoencoder. So first, we first train the autoencoder, and we replace aggregator of CTT with the encoder of AE. There are also some papers that instead of using the original autoencoder, we are Siamese use the rational autoencoder to improve the generalization. So for two sentences that are semantically equivalent, and we use a rational encoder to generate the dense representation Z, and which is the embedding of the tuples. Also, we can also replace there are also some one model Qt that replaces the decoder with classifier. So the classifier can be used to predict the next sentence of the similar sentence by using the CCT strategy. So but the main goal is to learning the sentence implementation or tuple implementation. This one. Okay, so now we already have the representation model, and how can we efficiently find all satisfied tuple pairs? So first, we transform each tuple to embedding, and then we use some existing existing cosine similarity join or Euclidean distance join method to find all tuple pairs, such as using some KN methods, LCH or product condition or some existing library. Finally, we discussed is widely adopted it uses the hash function and range implementation is more like the binary code because each element is stored 1 or -1. The second case is the IMA hash, which adopts the mutual information to improve the performance. So in the anti-blocking or anti-resolution area, BERT-ER is the latest work to combine the blocking and matching methods. For blocking, the idea is that we can use the matching model to assist to teach the blocking model, which we call the matching aware blocking methods. So we can see in the first equation, HT so T is the tuple, HT is the final binary code of the tuple, which is the binary representation of the tuple T. And this T is the dense representation, and X is the learnable hyperplanes. To make sure that we transfer each tuple is transferred to binary code, the loss function has three terms. The first is the L2 distance, such as if a tuple pair is matched, their L2 distance should be very small. The second term is contractile loss, which prevents very dissimilar pairs from commutation. The third terms are regulation for binary constraints. We also have some optimization methods, such as the binary code. The blocking should ensure independency of the hash base of the binary code. Here we use two strategies. The first one is a regulation-based approach, to make sure to achieve this goal. And the second one is that we use the SVD-based approach by decomposition the X using the SVD. Okay, the final framework is shown in this figure. The BERT encoder is the one component that to output the dense representations of the two tuple to U1 and U2. And anti-matching decoder will be discussed later. And in the blocking decoder, we use hash functions discussed previously to transform transform the dense representation to the binary hash code, so such that if two tuples are matched, so their hash code should be closed in the Hamming space. Okay, so now we already have the random hash model, so we can use the GPH, which is a paper method published in XD and TKD. So the main idea is adopt the pigeonhole principle and threshold allocation to efficiently find all satisfied tuple pairs. In summary, we have already discussed rule-based, machine learning-based, and deep learning-based methods. So for rule-based and machine learning-based methods, usually they do not need a lot of training instance but the accuracy are not very high and the running time are moderate. But for deep learning methods, because most of them most of them use a CMS network and use this cosine or Euclidean distance to retrieve the similar two pairs in the Euclidean space. So their running time is usually very fast, but they need a lot of training instance to make sure that the accuracy of the model. Well, but ER is the first learning hash model in the ER area, and its running time is very fast because it used the binary code instead of the depth vector, and it also has high accuracy because the blocking is.
So the problem of anti-matching is to find comparing the tuple pair. Usually the after blocking ones to find call references. So from a machine learning perspective, it can be modeled as a binary classification problem that output 0 or 1, indicating the pair is matching or not. So therefore, the evaluation metrics are also the ones that widely used in classification, such as precision, recall, and F1. So the trend of using deep learning as a backbone started from DPR, published on VLDB 18. So the model used representation, then comparison strategy that is firstly employ an embedding lookup layer of globe to transfer from the word sequence to the embedding sequence. Then use a LSTM model to aggregate the embedding into one vector. So each attribute is computed separately with a simple cosine similarity and then fit into a dense layer for final ER decision. So also the model uses a vocabulary retrieving procedure for the out of vocabulary word that come with no embeddings. So in this step, the word call occurred in the same tuples and from the same attribute are connected, and the initial values are assigned as the average of k of its most frequent call occurring words. So the performance of DPR is way better than the total non-deep solution Magellan. So Amazon Google dataset that has approximately 1,300 positive cases, it achieves an F1 score of more than 96%, which is about 10 points better than the Magellan. So another model is the matcher published on SIGMOD 18. So the general framework of the matcher is similar to DPR. So the major difference is that the matcher for the comparison, the matcher is not just use a simple scalar of the cosine similarity. So it uses a similarity vector that reflects the semantic difference between the two attributes. And this is achieved by a cross-encoding step that aggregates a tuple from its counterpart. For example, there is a tuple pair S1 and S2, and the cross-encoded representation of S1, namely S1 prime, is the attention-based sum of S2. Then the difference will be S1 minus S1 prime, and then it can be aggregated by Rn or LSTM and fit into a dense layer to output the final ER decision. So by default, the embedding of the matcher is fast-test. Although in the experiment part, they also claim that there are no big difference between fast-test and GLAV. So the experiment shows that on the refined Amazon Google dataset, the matcher achieves 69% F1, which is 20 points better than Magellan. So another model is Grapher, which use a graph-based method. This is the first one to explore the graph structure and apply the graph convolutional neural network to do the representation learning. So this setting is quite different from others that simply treat the tuples or attribute as a linear word sequence. So also the grapher proposed to use a token-centric comparison strategy. Recall that in DPR or DMatcher, they compare a pair of tuples on attribute level. So for grapher, the instructional information is softly embedded into the tokens, and the comparison is actually happened on the token level. The benefits are it's much fine-grained. It can share information between different attributes, and most importantly, there are no need for the schema mapping step of the conventional entity matching models. So firstly, the grapher built an ER graph that link tuple, attribute, and token together. And the edge weights are assigned with IDF between the tuple and the attribute, and TF IDF between attribute and tokens. And also the tokens co-occurred in the same sliding window are also linked. And this step is to mimic the behavior of the conventional skipgram model. And the edge weight between the co-occurring tokens are assigned depending on their data types. For example, they are textual or numerical. Then we apply a two-layer JCN to get the embedding. So the GraphER also employs the cross-encoding to represent the tuple pair. And after the cross-encoding, it's used a bilateral matching that compares the tuple pair in two directions, and use a two-layer heavy net for the final classification. So the performance shows that on the Amazon Google dataset, the GraphER model is about 8 points better than the DPR in terms of F1. So far, the deep learning model we introduced all requires large annotations, mostly due to the big model complexity of the heavy backbone. So there is a model called VAER. The aim of VAER is to reduce the annotation cost using some unsupervised representation learning. So for the first step representation learning part, it's unsupervised and it's achieved by some autoencoder model. And the supervision only used in the matching part. Also, for the third part is used an active learning trick to further reduce the leveling cost. So for the unsupervised representation learning, it uses a variational autoencoder that encode and restore the information of attribute in terms of LSA. So the learned encoding is more compact and informative, and also has a good transferability. So for the performance of VAER, it can greatly reduce the data labeling cost. It achieves a 90% or more F1 score with less actively labeled training data. Another interesting work is AutoML EM, which aims to automatically build an EM pipeline for non-expert users. So it relies on the backbone of AutoML, which input a search space, for example, a set of components like the data pre-processing, feature engineering, and model selection. To select which is an approximate model family, and also the hyperparameter settings. And also its input and evaluation metrics, for example, F1 and a time budget. It will automatically search for the best pipeline. So similar to VER, this work is also used the active learning trick to reduce the labeling cost. So in each round, it selects a set of unlabeled pair with lowest confidence score that asks a human reader to label them. The performance is less than 3 point worse comparing with SOTA deep metro model. So considering this model is much user-friendly, the performance is quite competitive. So another model based on the pre-trained language models is the DITA. So the DITA uses an interaction that which is synchronized, which means model has to feed a pair of tuples at the same time and get their deeply contextualized embedding. So for each candidate pair, the model adds special tokens, for example, COL for attribute name and VL for the value. And the two tuples are packed together to fit into BERT. So also the model would like to inject some domain knowledge, for example, the entity span and the span normalization. So as a BERT has a length limit of 512, so the model only picks the top 512 tokens according to the TF IDF. So also this model do some data augmentation tricks, such as randomly sample some spans from the token and swap the order of the two data entries to improve the robustness of the model. So in experiment, the DITA used the Robota as the backbone, and the model achieves 5 points performance improvement comparing the SOTA Metro Plus. So another topic is model ensemble. So the model risk furtherly train a base learner, then use a linear layer with some risk features to learn the residue between the ground truth and the predictions. They also claim that it can outperform the base learner with only 10% to 30% training data. So the current SOTA entity matching model is BERT-ER. So this model is different from the previous data model, which use an synchronized interaction. For example, given two tuple pair T1 and T2, so the data need to pack the tuple together first and then fit into BERT. But for the BERT-ER, so the difference is BERT-ER make the network CMS. So it encodes the tuple T1 and T2 individually, and use a comparison step to do the deep interaction. So the benefit of the CMS network is that so we have the individual encoding for each tuple, so we can readily integrate a blocking module to speed up the processing. So the core component is the delayed and enhanced alignment. So firstly, we found that the representation of our BERT can be decomposed into two parts. First one is representation, and second one is the interaction. So what we do is we wish to keep the representation part, but delay the interaction part to the comparison module. So also the interaction could be enhanced in 3 aspects. So the first one is we can use some explicit comparison features. And also we can concatenate the representation and alignment features to make them separating the parameters. And also we can employ some multigram convolution to extract some multigram features. So comparing with BERT, our model BERT-ER has a 2-point improvement. And most importantly, with a fast blocking module, it can achieve a 300 times speed up. So overall, horizontally, according to the encoder used, the entity matching model can be classified into supervised, for example, DPR, DMatcher, and the pre-trained LM-based ones, BERT-ER and DTER. And also some unsupervised ones like the VER and the handoff one, AutoML EM, and the ensemble ones, RISC. Vertically, according to on which level the two ports interact, we can see that the VAER and AutoML EM are on tuple level, while the DPR, DMatcher, and the RISC are on attribute level, and the graph ER and BERT-ER DTER work on the token level. Okay, thank you.